Let's get going with our investigation into alternating current. So what we've discovered so far is that when we use a generator, it produces alternating currents, and that will always have slip rings. Now that's an important feature. What you need to recognize is that you're actually, when you're using an AC generator, you're using mechanical energy over here, and the mechanical energy is being transferred into some form of electrical energy. And that's really useful. We recognize there's lots to know about the generator and how it works and why it works, but what are the advantages of using this sort of generator? Well, we know that it certainly has advantages over using batteries, electrochemical cells, because those electrochemical cells, well, they'll run out. The internal resistance will build up and the batteries will go flat. And so it's not sustainable to do that. I suppose we could produce direct current using a different type of generator, not an alternating generator. In fact, we can use a direct current generator. How would that be not as advantageous as this one? Well, the advantage to the alternating current generator is that it's safe to transfer electricity over a long distance. Now, usually we have power stations that are burning coal or burning gas, and we don't want those in the middle of a city. There might even be nuclear power stations, or there might be hydroelectric dams that are quite a distance away from the city. And so you have to take the electricity that's generated in these positions, in these places, and you have to transfer it closer to where everyone is living. And the secret of why we like alternating current is because it's easy to manipulate. And although we don't need to study and understand the process, what you need to understand is that if we've got alternating current in a coil and we bring another coil next to it, there will be a change in magnetic flux. And so that secondary coil is going to have an induced current in it. And that is the process of transforming. So a transformer, which you might go past if you're living in the city, you might see there are substations and there are transformers. Alternating current is easy to transform because it's changing. And because there's a changing electric field, strength of electric field, there'll be a change in magnetic field, and that will induce a current in the transformer. And so there are ways to make the current from the power station be transformed into a high voltage current, high voltage and low current process at the power station. And so in those grid lines that you see strewn across the country, we find that we've got high voltage lines and they're bringing a low current. The reason for that is we recognize that energy is lost when the current is high. Now, when you come to the city and you've got lots of houses, we can divide the current to make it smaller. So every house is in parallel with the house next door. The potential difference is the same. So we can use a low potential difference, high current, split the current into all the dwelling places, and in that way, we're able to use it safely. So in a city, we have a step down transformer that is used for the city, and we use a lower voltage and a high current that gets divided by each of the places that it's going to, each of the houses that it's going to. And so we recognize nobody's going to get hurt because the individual supplies, the endpoints, the current and the voltage are controlled. And so these are the advantages. The fact that we can distribute very easily, we can distribute safely, and we can distribute without energy loss. Now, as I've been talking about current and voltage, there's obviously a relationship between them. And I'd like to just take a look at that relationship by looking again at our graph. So there's an interesting idea here, and that is that we've got the time that I've indicated before, but we've got an ampere reading of current. And 15 amps is quite a lot of current that is being distributed. But recognize that that's not the maximum. So the maximum current happens at that point. And we would say that would be called I max. Now, what could we do if we were saying, well, this is alternating current. I want the equivalent of this to run a machine, and I know that it can run a machine on DC, direct current, and use up 2 amps. So how can I work out? Because 2 amps might be there and there and there and there, but how do I know what the 2 amps is? What's this overall change of current going to give me? Well, we can't really even do an average, because if we take all these values and we add them up, and we take all these values and we add them up and we add them together, we'll get 0. And clearly that's not very helpful. So we've got to do something a little bit cleverer. And the mathematicians or statisticians help us with this. So the first thing they do is they say, well, let's square these values. Now, if you square anything that's negative, it'll become positive. So it'll flip over. So the squared graph would look something like that. And we can now say, we've got the square, but we don't want the square. So what we can do now is to get the average, is say, well, let's add these together, and then let's take the square root of them. And so if we take these and add them together and divide by 2, so we take all of these values together, so we take I squared, and we take 2, because we're getting an average, because we've got the values, minimum, max, and then we'll say, well, let's take the square root of this whole thing. And if we do that, then we'll get I, that's on its own, over the square root of 2. And that is called the I root mean square. Now, that's a very important value. And we've got an equation for it where we say I max is that. This is the average value for current. It's the IRMS value. And whenever you get a machine and they say this is what the current it can manage, it's the IRMS. And in the same way, we can get voltage. And the voltage oscillates just the same as current, because voltage and current are related. Remember, power is equal to V times I. And we know even in Ohm's law that voltage and current are related. They're directly proportional to each other. So if the current is high, the voltage will be high. When the current is 0, the voltage will be 0. And so we've sketched on this graph the voltage. But notice something. Voltage potential difference. We recognize that this is more than one cycle. This is 1.5 cycles, so please take note of it. Take note as well that this value is 220 volts. That is in fact the value of VRMS under our normal situations. The V max is the maximum value, and it's slightly more. It's about 311, if I remember correctly, but we'll be able to do a calculation to show that. In the same way as we had IRMS, we've got VRMS over here, where we're looking at the average value for the voltage that is produced for alternating current. So please remember the difference between these and make sure that you're following that very carefully. Now, I mentioned power just now, and I think it's an important thing to recognize that power gives us a way to do some calculations, further calculations. And so I just want to highlight this for you. We know that power is the product of current and voltage, but over here, average power, which is always the thing that is given on an instrument. This is the rating of a machine. It's called the rating. So it will say to you that this is a 15-watt instrument. Well, that's the average power. And the average power is found by multiplying IRMS by VRMS. And if you do that, you'll see that it comes out to root 2 multiplied by root 2 is going to give you a half, and then it's going to be I max times V max. And that's quite a useful formula to recognize. And of course, we can use the other power relations that you've used for DC. You just need to recognize here that average power is not affected by resistance. Resistance is going to stay the same. So it's I squared RMS and V squared RMS that is going to give you the workings for average power. And so remember here that this is the same relationship or type of relationship that we get for any ordinary circuit. So having introduced you to these equations and this relationship between current, potential difference, and power, you know what? I think it's time to apply that knowledge. And so before we get into doing those sort of calculations, why don't you have a short break, get a pen and paper out so you can follow along as we try and solve some problems using these equations. We'll see you in a short while.